Okay, so we spent some time talking about 2 by 2 matrices and 3 by 3 matrices. Those are what are called square matrices because they've got the same number of columns and same number of rows. And in a square matrix, so long as the determinant doesn't vanish, you can invert them and write the system of equations, the solution solving for x in terms of y, pretty easily from the linear system of equations where y is a linear function of x. What about weird other shapes of matrices? What if I had only 2 x values but 3 y values? Can I write a set of matrix equations for that? Sure. Let's just see what that looks like. I could erase. Did I do that right? I did not do that right. Haha. Through the magic of pausing and restarting, I fixed my problem, but I decided to do it in color to show you exactly what's going on here. So if I eliminate the third element of that x array, that x vector, then it would require me to also eliminate this blue column from the 3 by 3s, because if I didn't, there'd be nothing to multiply it against. So, but the black first 2 could go into the 2 here. And so we start to learn something about the size of matrices. If I have an n by m matrix, and I do a matrix multiply times something over here, this had better be an m by p matrix. So m had better be the same in order for me to be able to multiply those together. If I could invert, for one of these, only if they're square, but I could take the transpose, and I could write first the m by p, but let's flip it around. I'll show you what that means in just a second. P by m, and then m by n. This one goes to there, this one goes to there. I can reverse the order of those matrices, but I also have to transpose them in order to get the same product out, but just swapping all of the rows for columns. What that means is I could have written this same array, but written first the x part, x1, x2, x3, but this is transposed, so it starts as a column, it becomes a row, and then I write the transpose of this matrix, A1, 1, and so see, it's 1, 1, 1. I swap the indices, so now the index is on the first one, and now A2, 1 doesn't appear here, it appears here at the top. And same A3, 1, A3, 2, A3, 3. And so you can either think of it as writing each of the columns copying from a row, or you can think of it as just switching the digits on the indices, because the one that was here ends up over there, and the one that's here ends up over there. So 1, 2 goes to the place of 2, 1, and 2, 1 goes to the place of 1, 2. Or A1, 3 goes to the place of 3, 1, and A3, 1 goes to the place of 1, 3. Okay. What do we get if we multiply this? Now we're doing a funny kind of operation because here's our columns. So it's a column times a row, plus a column times a row, plus a column times a row. And what we end up with is the 3 rows of this equation written instead as 3 columns of this equation. So this would be equal to y1, y2, y3. Now written as a row vector. So row vector, matrix, transpose, row vector gives us identical information to column vector, matrix, column vector, where here each of the rows in that column corresponds to one of these equations, and here each of the columns corresponds to one of these equations. But now let's return to our truncated problem where we dropped one of the x's out. So it's like we had just eliminated these terms from this set of equations. Well, hey, Does this still make sense? Well, yeah, I guess I could use different coefficients and come up with more than one y over there. But I've got 3 equations in 2 unknowns. So that means that something special has to occur for these 3 equations to make sense, which is one of these 3, at least one of these 3, has to be linearly dependent on the other 2. And we've actually already seen linearly dependent equations because when we added in our 2 by 2 system, we added the first equation to the second equation to cancel out some of the variables. The result of adding those 2 together was actually a linearly dependent equation that depended linearly on the first 2 equations that went into it. Here, this would be just fine so long as the third equation isn't inconsistent with the second or the first. If it's not, then you could, if you can figure that out, we're going to talk about how to figure out linear independence, but you could remove one of those that was linear dependent on the other 2 or on one of the others from the consideration, and then you'd have just a 2 by 2 system again. You could solve that, you can invert it, then you could add the other one back in as additional information and check to make sure it's consistent with the first 2. That's the plan of looking for linearly independent linear independence. So what we say is we talk about this as having a matrix rank. So the rank could be as much as the lesser of the two. So this is a 3 by 2 matrix, 3 rows, 2 columns. So a 3 by 2 matrix can have the rank of 2 or less if all 3 of these equations were linearly dependent. Or, for example, the simplest case, what if all 3 of these equations were the same equation with a11 and a12 equal to a21, a22 also equal to a31, a32, then they would have only rank 1 because there's really only one equation worth of information sitting there underneath. But if these were not like that, and say a11 and a12, a21 and a22 were distinct, then a31 and a32 can't be totally distinct, because if it was, we wouldn't be able to solve the subset of equations for y1 and y2 on their own and then just plug into the y3 equation and see. What's the thing that tells you whether a set of equations is linearly independent? Well, that's the determinant, that thing that we talked about before. So what's the determinant for this small set of 4? a11, a22, minus a21, a12. If this is not equal to 0, then that says that these 2 systems, those 2 equations are linearly independent, and you can invert those, just forgetting about the third equation altogether for now, and then the third equation, if it's consistent with the first 2, you could plug in the values for x1 and x2 you found from inverting those 2 and confirm that it gives you the same y3. If it doesn't give you the same y3, then you have an inconsistent set of equations. So the rank of a matrix could be as much as the smaller dimension, but it could also be smaller because it could be that there's really only one equation's worth of information in there. For a 3 by 3 matrix, the rank could be 3, or it could be 2, or it could be 1. It could be less than the rank of the 3 by 3. For a 4 by 3, it could be 3, 2, 1. For a 4 by 4, it could be 4, 3, 2, and so on. Let's think a little bit about what happens if, say, the second equation is linearly dependent on the first, but the third equation is linearly independent from the first and second. What would that mean? Well, that would mean that this same thing, but substituting in 3's for 2's, would be not equal to 0. This is if you could solve the set of the first 2 equations. This is if you could solve the set of the first and third equations, or you could do it with the second and third, etc. Good.